Hello everyone, welcome back to this channel. So this is James. Today we're going to talk about hardware and virtual machines, which is chapter 18 of A-level computer science. So let me just give you an overview of what we are going to cover. First of all, we're going to look at what control unit does and look at the two different types of instruction set architecture, CISC and RISC processors, some basic computer architecture, and followed by what is a virtual machine. Now let's look into the purpose of a control unit. It ensures that each machine instruction received by the CPU is handled correctly. So in Chapter 5, Processor Fundamentals, we talk about how the control unit is like the boss in the CPU. It directs instruction, it directs signal. So there are two ways that a control unit can be constructed. So first one is the hardwired solution. Construct the control unit as a logic circuit, and the machine code instruction are handled directly by the hardware, by all the logic gates. Another way to do it is to use microprogramming. So control unit contains a ROM component that stores the micro instruction or microcode for microprogramming. So these are the two approaches that a control unit can handle signals. Now, the second thing we want to talk about in this video is the instruction set architecture. So this describes the specification and attributes determining the instruction set, the format, addressing mode, and accessible register, governing the interaction between software and hardware in a computer system. So think of this architecture as how the instructions are being made. So is it a very long instruction, or is it a shorter one but simple? So that's what's the difference between CISC and RISC afterwards. And then every processor will have its own instruction set architecture, and the choice of instruction is the main factor distinguishing one instruction set architecture from another. So now let's look into two different types of design philosophy when it comes to designing an instruction set. So an instruction set is basically a group of instructions that a CPU can use in their operations. And the two instruction set philosophy, CISC, stand for complex instruction set computing. As implied by the name, each instruction set here is a lot more complex. And reduced instruction set computing is simple and more streamlined sets of instructions that require minimum loading of data from memory. So I have created a diagram here to illustrate. A complex instruction can execute 3 tasks at once, whereas a not so complex instruction can handle 1 task only. So of course there are benefits and disadvantages for each design philosophy, which we'll look at it later. But then let's continue to compare and contrast. CISC often vary in length and complexity. Look, because the philosophy is that each instruction should solve as many stuff as possible, therefore their instruction length can be different. Maybe this instruction set 10 bits, the other one 16 bits. Alright? But then for reduced instruction set computing, because they favor a simple instruction, this means that they can simplify their instructions in a way that all instructions are the same length. So I give you an example here. x86 processor from Intel and AMD, they usually uses this philosophy, and ARM uses this philosophy. But one key takeaway from this video should be that there's no one-size-fits-all solution. In fact, modern CPU chip designer, they often incorporate complex and reduced instruction set and try to find the balance between it. Okay, so it's something to take note. And this is how we compare and contrast the two in just one table. There are more instruction in complex instruction, fewer instruction, more complex, simpler, many instruction formats, small numbers. So you can see that even though the instruction in RISC can't do as much as complex CISC, but they're a lot simple, meaning that the designer of this, whichever CPU chip that uses this, will be easier. It will be easier for them to implement it. Fixed length instruction, variable length, single instruction cycle, multi-cycle, many types of instruction to address memory, only load and store instruction to address memory. So that's the very big difference, because these only have 2 instructions to do this thing, and they have many different types of instruction because they want complex. More addressing mode, fewer register, multiple register set, so on and so on. We'll talk about pipelining in a while. But From now, you should be able to see what the complex here mean. It basically means that each instruction is very specialized to solve just one task. Whereas reduce here is stand for reduce in complexity. Okay. Now, pipelining is something that the RISC can do. All right. So I will talk about what it is in a while, but then let me read the definition. It enables pipelining due to simplify and uniform instruction set, facilitating regular instruction execution stages with consistent instruction format and reduced complexity, thus allowing efficient overlapping of successive instruction in the pipeline. So I'm going to show you a diagram to show you how we can make a CPU faster by using RISC. So if you don't remember, this is the fetch, decode, execute cycle, and these are the different cycles that are in the these are the different steps that are in the cycle. So what RISC can do is that at one particular time cycle, they can execute the many instructions at a time. So let's look at this. So this is the pipelining sequence, and on the x-axis here is the clock cycle, and y-axis here is what each component in CPU is doing. So at clock cycle 1, you can see that only the first instruction, 1 means that the first instruction, 1.1 means the instruction fetch stage of the first instruction. Okay? And at the first cycle, 1.1 is running. But at clock cycle number 2, you can see that the instruction fetch, since it has been done, now it's at the decode cycle. So the decode component will do instruction 1. But then the instruction fetch component can start taking in new instruction to do the first step of instruction 2. Clock cycle 3, clock cycle 4, clock cycle 5. And what happened when time cycle equal to 5 is that the processor is handling 5 stages of 5 different instructions at the same time. This speed up the processor 5 times. So you can see that at this particular moment, in a conventional sequence, they might take 5 clock cycle to complete just one instruction, 1.1, 1.2, 1.3, 1.4, 1.5. But what happened is that by making the instruction simpler in RISC, at each clock cycle, the component that is idle, they can take in a new instruction straight away. So if you look at from time cycle 5 onwards, the processor is currently multitasking. This is what we call parallel programming. So of course, issue with pipelining is how do we handle interrupt? Look, it's usually occupied, but what if we have an interrupt to handle it, like a printer out of paper, out of ink? So there are 2 options. First one is to clear the pipeline data related to the 4 most recent instruction, meaning we basically just delete the instruction so that we can handle the interrupt. The second option is to build separate units within the processor, each with its own program counter per register, enabling the retention of current data, meaning we keep it first in another register, and then we handle the interrupt, and then after the interrupt is handled, we come back to the data. So this is how we handle it. Now, so that's the difference between CISC and RISC. So now we're going to look into what are the different computer architecture we have. So these are the 4 different types. It's not so hard to understand because the name actually implies the philosophy of the instruction set. So single instruction, single data means that one instruction can only handle one data at a time. For example, I have an array here, and if I want to multiply 3 to each number in the array, instruction 1, multiply 3, instead of everything being multiplied by 3, only the first one, because it only acts on single data, one instruction, one data. Then second one, 3 to 9, and then 4 to 12. So that's how we do in SISD. It's pretty simple, single instruction, single data. Another second one is what we call single instruction on multiple data. And this is when single instruction is executed simultaneously. So this is the instruction, and they are being inserted into processing unit to operate on the same data. So one example is this. Instead of multiplying the data one by one instruction can be applied to multiple data, and then the output will be here. Okay. So now Implementing single instruction multiple data. One approach utilizing computer is known as arrays or vector processor, featuring parallel register, each designated for a specific data stream. Okay, and another approach involves employing larger register capable of storing multiple value concurrently, integrating parallelism. So parallelism basically is how we handle multiple data at the same time in this case. So they say there are two ways you make many register or one big register that allows parallelism. Okay. Conversely, multi-core processor involves separate processor operating simultaneously, with each likely having its dedicated cache memory. Alright, so this is how it is implemented. And the next computer architecture is the multiple instruction, single data. According to the book, they said it's a hypothetical data, which means that not a lot of processor uses it. But an instance that I can find is a fault-tolerant system where identical data, same data, is being instructed multiple processor, and each processor will run different instruction. Yeah. Okay. So that's multiple instruction, single data, not very common. Next one, last one is multiple instruction, multiple data, similar to SIMD. The only difference is now that the processing unit does not execute the same instruction. So you can see from this diagram, different PU processing units getting different instruction, and they are also getting different data. Okay, so this is how it looks like. I have different data here, and followed by different instruction. Instead of multiplying by 3, there are 3, 4, 5. So let's look at massively parallel computer system. This is a system based on MIMD architecture. They have a lot of processing unit, crucial in supercomputer for tackling complex computational tasks at an immense scale. So supported by a network infrastructure, linking multiple computer units to facilitate communication and coordination among them. So this is when we have multiple processing unit, each of them taking data, multiple data stream. Another one is cluster computing, a system architecture where multiple computers are connected, working collaboratively. So it's called cluster because you're clustering the processing unit in multiple computers to solve one task. Okay, now the last part of this chapter is called virtual machine. It is a software, all right? It's called virtual for a reason, and they can emulate a physical computer and run application as it were a separate or independent system. So a system virtual machine emulates the hardware of a real computer system. The keyword here is emulate. It pretends that it is something else. So I will show you how virtual machine can be useful later, but let's look at how the structure is like. Okay, so now let's start from here. Host hardware. For example, I'm using a Mac. Therefore, I'm using Mac OS. So what I can do if, let's say, I want to run Windows on my Mac, that's when I can install a virtual machine software. And this virtual machine software will allow me to install multiple virtual machines. Maybe I can install Windows and Linux here. And then on my Mac, I will then be able to access the operating system. For example, Windows operating system, Windows 11, or Linux operating system. And with that, I can run application that cannot be run on Mac, but can only be run on Windows. And that's all made possible because of the virtual machine, which is a software that allow my computer, which is a Mac, to pretend to be like a Windows machine, to pretend to be like a Linux machine. Okay, so application program is installed with the assistant of Gas OS. Gas OS is not the OS that Apple gave me. And then virtual machine is considered a utility program supported by my host OS, which is accepted by Mac OS. And then other application program can run simultaneously on the host software. So this is something I do during my university time. Remember, they gave us an assignment that I must use Linux. But then at that time, I only have a Windows computer. This is why the lecturer asked us to install a virtual machine. And of course, the advantage of a virtual machine like that is that I can run more than one OS. So at the time, I am able to use my Windows computer to run a Linux program. But then the disadvantage is, this is not my disadvantage, the implementation of the virtual machine, they will need time and effort. But then this is also what I experienced, is that the computer performance is not so good because they are not the legit original OS. So to show you a diagram, this is what you can do. A Mac OS, so you can install a virtual machine that allows you to run Ubuntu, Linux OS. So that's the end for this video. We talk about hardware, the different instruction set architecture. We also talk about what a virtual machine can do. So that's the end of this video. Thank you so much for watching. I'll see you in the next video. Goodbye.